Hello everyone, welcome and thanks for waiting. For everyone who's been waiting patiently while we've been letting more people join this session. My name is Honey Lux and we are broadcasting from Cullen, from UKAEA. And as you will all be aware, this is a session as part of the Energy Security and Green Infrastructure Week. I'm sure some of you will have been listening to session yesterday or today, or will be continuing with more of them tomorrow. So welcome to our UKAEA webinar on the future of fusion. Today we've got 3 speakers talking about different aspects of fusion, and we'll be starting off with Debbie Kempton, who is the Director of the Engineering Programme for the STEP programme. So STEP programme, Debbie will explain to us more what that is and what that means, but she has only recently started 4 months ago at UKAEA working as the Director of Engineering for STEP, but she comes with 30 years of experience in other engineering projects. So welcome, Debbie, and without any further ado.
Thank you, Hanny. Thank you very much. And thank you all for having me today and for allowing me to speak today during Green Infrastructure Week. So I think without further ado, we'll get started. I hope you all will forgive me. I do have some speaker notes, otherwise I will just rabbit on for ages. So this helps keep it all a bit focused. So as Hanny said, I'm the Director of Engineering for STEP. I was 30 years in aerospace and defense. And my talk today is deliberately not technical. You're going to, a lot of that maybe throughout the rest of the week. What I really want to do is come at fusion from a more human angle. So if you like to get technical on what the AEA and what STEP in particular is up to, we've been to loads of conferences recently. We've been to SOFI. We've just been to the Fusion Energy Conference in London a couple of weeks ago. There's lots of stuff in the public domain, and you know the talk coming up just after mine will be a bit more technical. But so instead, again, my focus is going to be more on the positive impact of fusion energy, and specifically looking at that human impact. So right, with that, let's get started. Back in the day, Stephen Hawking was asked, is part of the big questions, what would he give to the world if he could give them anything? And his answer was, if he could give the world one world-changing thing, it would be fusion power. And I can totally see that, right? It would be an amazing gift. Imagine what we could do with unlimited clean energy. It would be absolutely fabulous, right? And who wouldn't want to give that gift to the world? Why is that such a gift? Because we all know the benefits of fusion, right? It's low carbon, it's safe, it's reliable, sustainable, we get energy efficiency out of it, and it's a big part of addressing climate change. And from the human perspective, climate change is something that worries lots of people, right? Climate anxiety is a real thing, and it affects all age groups from the very young to the very old. So the obvious benefit of fusion power is a positive impact on climate change. Right, but it's not just about the power plant, right? The journey to fusion power is just as important as the destination. Getting to the fusion plant will be a journey of discovery, but it's also a journey that's going to provide a net positive impact on multiple fronts. And you're probably wondering then, why do I have a picture of the moon up there? What's the moon got to do with fusion? So let's think about the moon landings for a minute, because I think they're a really good analogy of the journey that we're on. So Kennedy, back in the day, famously said, we choose to go to the moon in this decade and do other things not because they're easy, but because they are hard. And fusion power is indeed going to be hard, just like getting to the moon. It will push science and engineering to its limits, and it will further science and engineering. Doing that is always a laudable goal. But there's a second part to that quote that is a little bit less well known, right? So why do we go to the moon? Because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we are willing to accept, and more importantly, one we are unwilling to postpone. So that challenge, that fusion challenge for us, is definitely one we are willing to accept, and one we shouldn't be willing to postpone, because it matters, and it matters in a lot of ways. It's more than just the laudable goal of advancing science and engineering and technology. So let's just take a minute and let's imagine what that fusion journey might look like, right? So if we reflect on the Apollo program, they didn't just put a man on the moon. Apollo spun off lots of things like thermal blankets, shock absorbing trainer soles, which my dodgy back thanks them for every day. They fireproof cloth spun out of Apollo, and firefighters thank them for that every day. The insulin pump, scratch-resistant lenses, eye tracking technology that's now a fundamental part of LASIK surgery. And think of the millions of people that benefit from LASIK surgery. We got better water filtration. We got digital signal technology that led CAT scans. We got memory foam. We got integrated circuits. We got Teflon, which I'm hugely grateful for because I'm not the best cook. And we also got Velcro, which many school-age children are hugely grateful for because it makes getting their shoes on and off really easy during the day. So Apollo had a net positive impact on humanity in health, in safety, in comfort, and in general well-being. And it was also a huge boost to the economy, employing something like 400,000 people over 9 years, and that was just to get to the initial moonshot. But just like Apollo, fusion development is going to do more than just make a power plant. We're pushing the boundaries of science and technology, and that's going to lead to new discoveries and new applications. But we're also going to create jobs. We're going to develop infrastructure. We're going to create new skills, and we're going to advance current thinking. And it will also inspire a generation, just like Apollo inspired many of us, well, certainly many of us of a certain age, to get into STEM. The development of fusion will also do that. So you don't have to imagine that we can do these things as part of the fusion journey, because we will. And a major part of that is the STEP program, which I will come on to next. So what is STEP? Right? STEP is the spherical tokamak for energy production, and it's a prototype fusion power plant. And it's intended to demonstrate a path to commercial availability. So it's a prototype, but it puts us on that journey to full commercial power plants. It's going to be located in West Burton, and we're repurposing a coal-fired power station. So by using a brownfield site, we're not only respecting the environment, but ensuring the local community continues to thrive. West Burton's an absolutely fantastic site. It's about 330 hectares, and it has the opportunity there to grow that whole ecosystem that will sit around STEP and around the plant. It's a place for businesses to develop and for that region to be a global hub in fusion and beyond. And we also have incredible local support there, for which we are very grateful. The third thing, STEP, is it's a partnership, right? And it's a long-term vision. Whilst there's a commercial partnership between government and industry, there's also an equally important partnership between STEP and the local community. So we're basically coming into their home, and we really want to be good neighbors. And finally, on that chart, I think from the little Gantt chart, you can get an idea of the timelines for the program. We're finishing up the initial concept phase now, getting ready to move into more detailed design. And honestly, we're constantly learning as we go. So in terms of key objectives, I mean, that was a bit of overview about STEP itself, but what are we trying to do? What are our key objectives? Obviously, the physical deliverable is the prototype plant, right? That demonstrates the path to achieve our critical commercially relevant features. That plant will then be available for the broader development of fusion technology. It'd be absolutely inconceivable to spend billions of pounds on a prototype and then not be able to leverage that facility for future use. And indeed, we're taking a big leap from the JET playbook and learning from the JET designers. So we want to enable the plant to be changed and developed beyond the immediate requirements, just like JET did. And by delivering that plant, we're also going to establish an incredible information baseline. And that's not just the technical data and what decisions were made and why we made them. It goes beyond that in terms of thinking about the program delivery and the actual costs. And that's going to be an absolutely key source for future development and optimization. So how do we do better for STEP 2.0 and STEP 3.0 and onwards? So continuous learning and spiral development as we go. And those three things, are super important and well worth doing all by themselves. But we get more than just those things by doing STEP, right? We also get, we get economic value, right? We grow an industry. We'll develop capability in the supply chain to deliver fusion commercially. And we also want to involve our suppliers in the very heart of the design. And that way we build sort of real capability in the supply chain. We also, in terms of economic value and jobs and commercial contracts, We've got innovation in regional development, but there's also going to be all of the spin-offs in the technology that goes beyond fusion, a bit like what Apollo did. And finally, and for me, this is probably best of all, it's the social value, right? In particular, in the area around West Burton, where we'll drive that transition from fossil to fusion, we'll also be delivering value more generally in terms of skills and education and training. And don't forget that inspiration piece, right? By inspiring a generation of young people and encouraging them to take up STEM careers, that's both a positive outcome, both socially and economically. And it will also help address some of the skills shortages we see in the UK in science and engineering. I just wanted to have a few examples of some of the economic and social value that's already been provided by fusion. So if we start sort of in the top left of that slide, and we look at what's happened at Cullum, right? So in sort of the last decade or so between 2009 and 2019, the equivalent of 4,000 jobs a year were created by the fusion programs that we're doing in Cullum. The UK economy gained 1.4 billion due to government investment. For every £1 invested at the AEA, 4 was generated in return. The UKAEA, we've opened up an apprenticeship academy. And now we train 350 technicians a year, and we do that not just for us, but for 20 other local companies. And fusion research has produced all kinds of technology transfer into the wider industry, things like robotics, materials, computing, and artificial intelligence. So that's sort of a pedigree for what we've done, and that's relevant because we see the similar types of advantages and benefits in the West Burton area as we go forward with STEP. We're going to be creating a whole new supply chain, investing in R&D and creating jobs. And this is long-term employment opportunities, long-term demand for a variety of skills and the education and training providers to go with them, and decades of demand for a host of goods and services, both to support the build and the commissioning of the plant, but also to service that plant while it's operational. And then finally, looking in that little yellow box, we've already been engaged with the local community. And I said before, we've had absolutely fantastic support from the area. But we want to help them understand what this means, to and for them. So when we went to Retford, that was the 4th community event we've held. We do them roughly once a quarter, and we absolutely plan to continue doing that as we go forward. It's an absolute pleasure always to go into the local community. Like I said before, we want to be good neighbors, but more importantly, local insight is really invaluable when we're doing something like this. So as much as sort of the local community learns from us, we learn from them, right? And that makes it a real partnership as we go forward. So fusion in general, and STEP in particular, it means jobs. It means investment. It means skills. It means new industries. And it means new science and learning. And it also, most fundamentally, means working together. Finally, just a bit of thinking about our Apollo journey and where that could end up, right? What the future applications might be. This is a really high-level look of maybe some of the places that fusion technology could take us. The first and obvious is robotics, right? All of the things we learn about remote handling, remote modeling, will have applications in lots and lots of fields, whether that's space or deep sea exploration or anywhere, really. From a materials standpoint, there's new materials to be discovered, new applications of existing materials, or better understanding of performance at extreme temperatures. We can then take all of that and think about new structures that might survive in other harsher remote environments. We'll also discover a load of new construction techniques and find new ways of doing things like shielding. So there's lots that will happen in the material space. From a digital standpoint, there's no doubt there's going to be advances in modeling, simulation, computing, artificial intelligence, machine learning. We're going to have to invent new control systems. But where else might some of this stuff apply in the future? As I said, machine learning and AI is definitely going to be part of the mix, as will be our ability to create and maintain a digital twin of the power plant. And that digital twin, won't just be the as-built configuration, but it'll be all the models and all of the knowledge that sits underneath that. And that's going to allow us to run things like what-if scenarios and performance. And that process, how we get to there, how we do that development, is relevant to loads and loads of different industries. Getting to a digital twin is critical, not just for us, but really, really helpful and really critical to lots of other industries. And we're also going to break new ground on things like remote sensing. So how do you do built-in test and evaluation in really harsh environments? So all of that is also useful in lots of places. Finally, skills, right? We're going to develop skills. We're going to advance skills in existing disciplines. We're going to create suitably qualified people that can transfer their skills into other industries. And some obvious upskilling, will happen in the areas of systems engineering, electromagnetics, computational fluid dynamics and plasma physics, civil and structural engineering, cryogenics and containment and magnets. So over the next 20 years, right, just think about where else our Apollo-like spin-offs might take us. We really, really just can't know. There's just so much to learn and discover, and absolutely every day is a school day on the STEP program. But all we can know is that it will happen. I can absolutely guarantee that Neil Armstrong, when he was on top of the Saturn V, strapped up there in the thing, was not thinking about memory foam integrated circuits or thermal blankets. But somebody was, right? And somebody will when we talk about fusion. Right, so in summary, you know what? Fusion's cool. It is. It's just cool. But it has an impact that is so much bigger than just the science. It's a positive impact on the economy, on education, on skills, on jobs, on knowledge, and most importantly, it's a positive impact on people. So I guess my ask would be, as you go through this week and you listen to the green infrastructure things, think about the impact that we can have, why what we do as scientists and engineers matters. Because there's no doubt that science is cool in and of itself, but it sits in the context of a wider world that is positively impacted by what we do. And I'll leave you with one final thought, and I'll apologize to John F. Kennedy for taking liberties with his quote. But we should choose to pursue fusion, not because it is easy, but because it is hard. Because that goal will serve to organize and measure the best of our energies and skills. And because that challenge is one we are willing to accept and one we are unwilling to postpone. So there's no doubt that fusion, and green energy in particular, is hard, and fusion is really, really hard, but we should accept the challenge. We should be unwilling to postpone it and bring the best of our energies and skills, because the benefits beyond the science are well worth reaping. And that's me. Thank you very much.
Thank you very much, Debbie. Just as everyone will have seen, questions are allowed to be put into the chat. So if you've done that already, thanks very much for the questions that have already come in. Anyone else who's got any questions for all the speakers, feel free to start putting the questions while they're talking. But we will be having a couple minutes questions afterwards as well. So if you come up later. So for example, Tim has previously asked a question about the spin-offs and spin-off benefits. He asked that question a little bit prior to you talking a lot about that already, but I think he's just been saying, are there any specifics known yet already from the STEP program in terms of spin-off benefits that we've seen?
I think, we're still in conceptual design, right? So I don't have a tangible piece of hardware that I can point at and say, we did this here and now we can spin that off there. I think, it's very clear that there'll be things with robotics. We see that with what the work that RACE does in the wider authority. That's exactly the kind of approach we need to take, just like JET did in terms of remote maintenance. So there's no doubt, as that technology evolves, there will be spin-outs out of that, no doubt. I think the other big piece will be in materials. We operate at significantly higher temperatures, and many times we're trying to do the engineering and we're off the temperature curve for normal materials charts. And that's interesting, right? So I expect we're going to learn things about materials and about how we can do different things with structures and operate in harsh environments that, as we go through, even through the conceptual design and do coupon testing and some of that should start spinning out information applications, as we go. The digital twin thing is also probably something that's going to be an earlier win, because it's one of the things that we need to start as we mean to go on. So we're really getting quite hot on developing that. And that process, again, it's not the fact that we have a digital twin for STEP, it's the process for how we get there. And we'll be able to spin that up, I think, reasonably quickly.
Yeah, thanks, Debbie. So thanks for everyone who's already been putting into the chat where they've come from and what their background is. That helps us a little bit gauge what what audience we've got. And we've seen some very deeply technical people being there, but we've also seen school students participating, which is really great.
Lovely.
So Debbie, a very brief question for you, because you've mentioned JET a couple of times, and surely for some people who've been following fusion, that will mean something. For people who are coming new into fusion, might have never heard about JET. Do you want to briefly say something about what JET is, what it was, and why it's been so important for fusion?
Yeah, I can, though I probably need a bit of help from some of you who have been at the AEA longer than I have. So JET was the, I'm going to get this right, Joint European Toroidal, right? It was a collaboration between many European countries. Is it 1982? I was going to say 7. I'm looking at chief engineer in the back, right? 1982. So it's been running for, gosh, how old am I? 40 years, right? It's been running for 40 years. So it's a different style of tokamak to step, but it's been at the forefront of fusion energy and fusion experiments for a long time. And if there's a follow-up question to that, I'll point at Chris, who's going to come on next, and he can cover that. But yeah, it's been really, really good and really useful.
We unfortunately have fusion people, really advanced fusion people in the audience. Thanks, Robin, First Plasma 1984, for correcting us.
Yeah, so, First Plasma 84, but
yeah.
Yeah.
Thanks for those comments. I'm just trying to see, I thought there was another question. Sorry,
there's one that's popped up on the board. Can we elaborate on the apprenticeships? What areas are we looking into? A lot of areas. So similar to how we've set up the Apprenticeship Academy in Cullum to support the Cullum site, we're looking at an academy up toward at the West Burton site. And it's everything from level 2 apprenticeships all the way up through level 6 and 7. What does that mean? So your level 2 and level 3 are more like your technician apprentices. So, welding, CAD driving, being able to do designing, drafting, that kind of stuff, all the way up through level 7 being sort of your degree apprentice. You end up with an engineering degree at the back end of it. Level 7 is, level 6 is bachelor's, level 7 is a master's degree. So we're looking across the whole swathe of apprenticeships, but really we want to get people into technical careers from everything from manufacturing of the plant, building the plant, commissioning the plant, operating the plant, doing support and servicing as we go on, but also some of the engineering that we need to do, both to optimize the plant. It's sort of 10 years or so from now before we start, any of the construction, and it may be 20 before we actually turn on it, because it's a huge piece of critical national infrastructure. But so it's apprenticeships in everything from manufacturing to support to services to engineering degree type apprentices. It really is quite a broad umbrella that we're trying to, or a broad shadow that we're trying to cast.
And if people are looking at apprenticeships or careers in fusion going forward, would you be recommending to focus at UKAEA, or do you say are there any other surrounding environment where people can look and if they're interested in careers in fusion?
Oh gosh, I would always start here, I suppose, because essentially we're sort of like the national lab, aren't we? And I think Kate's just putting up something in the chat around further information. Drop a note to events at UKAEA. But there are lots of apprenticeships available all around the country. And there's nothing that says that you can't start an apprenticeship now. So if I was 16 or 18 and I was interested in getting into fusion, lots and lots of skills are transferable. So don't feel like you have to come to Cullum, right? Get into an apprenticeship, think about what you want to do, and then start thinking about then either maybe you transfer as part of as an apprenticeship, or you take a stretch assignment someplace, or you get your first job when your apprenticeship is done into fusion. But there's loads of apprenticeships available, and lots of the skills are transferable.
Thank you. We've had another question from Tim, who said, when do you think that STEP will be gathering momentum, and when will construction start?
It's already gathering momentum. We've got quite a large number of people working on the program now. hence bringing in some of the new directors and some additional staff. We're about to start a commercial process where we look for partners. So that's going to launch very soon. Construction is probably about 10 years away, right? It's probably there or thereabout. But there's a lot of design that has to happen first. Safety cases, making sure it's safe, secure, fit for purpose. So there's a lot of work that needs to do. Basically, we're designing a power plant from scratch. Then there's lots of lessons you can learn from the fission world, but fusion is fundamentally different from fission. So yeah, I'd say about 10 years we'll break ground. But there's, again, in that 10 years, there's lots of stuff happening at the West Burton site, which includes decommissioning the existing coal-fired power station and then doing all the environmental surveys and all of the getting all the permissions and everything like that, and that takes time as well.
Yeah, I think that is a perfect time to hand over to the next talk, because our next speaker is Chris Walden, who will be talking a lot more about the details of step power. Thank you very much, Debbie, for joining us and for answering the questions.
Thank you very much.
Yeah, so our next speaker is going to be Chris Walden, who is the Chief Engineer and Deputy Director for the STEP programme here at UKAEA. And he builds on that role in a range of engineering leadership roles that he's held over the past years at UKAEA. So welcome, Chris, if you want to join me. And Chris will be talking about delivering a first-of-a-kind fusion power plant, that is STEP.
Thank you very much.
All over to you.
Okay, so the good news is that we know fusion works already. We've got a natural example in the real world, which is the sun, and here at Culham it's not that visible at the moment. It's shrouded in rain clouds, but trust me, it really does work. And fusion, the process that powers the sun, is where we've got this hot ball of gas, and it's hydrogen gases, a makeup of lots of gases actually, that's at this fourth state of matter, which is plasma. So you've got a solid, you've got liquids, you've got gases, and then you go into plasma. So you have this ionized gas that's at very high temperatures, so high temperatures in fact that they go into positive and negative ions, and they're running around really, really, really quickly. So quickly in fact that when they get close to each other, they overcome that natural aversion from each other and smash together. And this is when you get fusion occur. And you get the release of energy in the form of a very fast neutron and some helium as well. And this is how it occurs. But it's like a fusion power plant, if you like, up there in the space. But it's quite an inefficient one. And to get to the efficiencies we need to here on Earth, because they've got gravity, obviously that helps, we need to get to 150 million degrees C, where the sun itself is 15 million degrees C. So that's quite a eye-watering high temperature, and because it's positive and negative ions, we've got a chance to control that hot gas by using magnets to confine it. So that's one of the key aspects. I'm going to be talking to you about fusion and using magnets and magnetic confined plasmas to produce fusion energy. So a good starting point, I think, was just to think about what are those key ingredients we need. So from the technical requirements to what our stakeholders what they want. So obviously, just like a power plant, you want a highly controlled plasma as your starting point. You need those robust magnetic cage to hold it all in place. You need to be able to convert that energy into power, and we do that using, and I always think this is a bit of a weird term, but we in the fusion community call them blankets. So that's like the inner lining of the machine that converts that fast moving neutrons into thermal energy, and it also, as another function, converts some of that energy through a process into the fuel itself, tritium, which is a part of the fuel we use in the process. We want the materials to be able to live for a long time. We don't want them to wear out very quickly, so we want long-lived materials. We want this self-sufficiency that I talked about in the breeding blankets, so the tritium fuel cycle. And we want architectures that allow us to maintain these machines such that it's not like a ship in a bottle, so to speak. We're able to go in and maintain the machine as it slowly ages over time. And we need we could have a great technical solution, but we need the cost to be such that it's not prohibitive for people to invest in the technology. And then from a stakeholder's perspective, you need a safe, predictable power source. We need things to happen now, not later. I don't think our environment can wait for much longer. And we need credible costs. And I'm not just talking about the initial investment, we're also talking about the total cost. You know, Space Shuttle was a great technical solution, but its operational costs meant that it was slowly retired over time. And we need to be able to convert that power efficiently into electricity, or maybe even to hydrogen, or even industrial heat source. So again, that's being able to convert this energy into something that's usable for us. And we need to be able to manage the waste, because there will be waste products. And just as Debbie was talking, she was making me smile a lot with all of her benefits from the space program, and Velcro and things like that. We need to be able to, because there's going to be a reasonably long gestation period before we have a technical solution. We need the side benefits already in advance to help that journey. So you hear us talk about tokamaks. Tokamaks, I don't know if this is particularly true, but it means Russian, in Russian means magnetic bottle. And there are various different solutions that we have in the magnetic confinement space. We have conventional machines, which are on the right-hand side here, which is the, let's go back a slide. In the conventional space, which is jet, a conventional aspect ratio, which is more of a donut shape. And then on the in the middle, we have the spherical, which is a tight aspect ratio. So think of it more as a chord apple. And if you think of the magnetic fields, the effectiveness of those fields drop off 1 over R. So it's slowly, the closer you can get the magnets to the center of the machine, the more effective you get use of those magnetic fields in the process to enable us to realize the energy. So that's the benefit of a spherical tokamak. And on STEP, we're trying to really focus on not just the one aspect of the machine. We're looking about all of it's about getting energy onto the bars and to the national grid. So it's all of the energy from if I equate it to like a car, starter motor, so taking energy off the grid to start up our reactor, and then all of the inefficiencies. So we're trying to maximize the efficiency of the generation of the power source, which is the plasma, and then minimize on all of the parasitic loads, so the internal, if you like, hungry systems that want energy, and maximize it all the way out to the energy out on the other side out. And again, this is where the spherical tokamak is so useful, in that it does that in a very neat and efficient way. And if you look at that tight aspect ratio, the benefit from that is it's a reduced size machine. So if you imagine you draw a horizontal line through that tokamak in the middle of the diagram there, you would get an idea of what the cross-sectional makeup is. And that diagram in the box on the right-hand side shows the difference between a conventional machine and a spherical machine. And you can see you've got 8 meters roughly, broad brush, diameter machine, so 8 meter radius machine. And then on demo, which is the conventional aspect ratio for a conventional power plant, it's up the region of 16 meters. So it's quite a significant difference in cross-section. It gives you an idea of size differences. And if you think that we're using very expensive novel materials, then that size difference makes a difference in the overall capital cost. So what we're asserting with a reduced size machine is a reduced cost machine. Equally, because we're using reduced fields, the magnets, we are able to use these picture frame magnets, which enable us the access and egress into the machine to maintain the internal parts. But it doesn't take too much thinking about to think, well, okay, you've made the machine smaller, but it's got a certain size, energy size, so you're spreading that energy over a much smaller area. So it's much more challenging from a technology perspective. So I'm really challenging, leaning into the technology space. And again, that makes it very much closer to a commercial reactor. And overall, it's no good me having 1 or 2 solutions. It has to be a self-consistent concept, and that's why having something as an aiming point, and actually us trying to do this for real in a conceptual study as we are in STEP right now, it makes us have an integrated solution. And that's part of the magic, is solving all of the problems. It's also a nightmare as the chief engineer, because you're trying to do all things for all people. But anyway, if I start to then think about, and again, I've got all these hooligans that are trying to pull on me in different aspects. I've got the plasma chefs who have certain key recipes that they're trying to create the plasma in the center of the machine. And I've got the engineers who are trying to realize the machine on the right-hand side here. So if I look in the middle here in this little circle, I've got all the functional design that I'm trying to, got this tension between these two communities. I've got the plasma physicists who want high, strong magnetic fields. They want big, large radiuses and high heat fluxes spread over the internal surface of the machine. The engineers are saying, no, 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 no. We want low fields. I want low heat fluxes on the machine, and I want to make it small. I want a small radius. So somehow I've got to find this balancing act. And then on the bottom part, which is the spatial design of the machine, can I get it all to fit together? You know, you want technologies that are a small step away from where you are right now. So you want low complex, low novelty. And again, on the left-hand side, you've got all of the, if you like, the programmatic people that are saying they want a cheaper machine, they want it more realizable. So you've got all of these competing people, and I feel like I'm on that hamster wheel in the middle there, and I'm trying to satisfy everyone. And again, it is a balancing act, and I guess my job isn't done until all of the audience are unhappy that they've had to compromise in some way, but at least we found somewhere that we've managed to juggle this balancing act. And coming back to those key stakeholder requirements, this is my guiding compass, if you like, that's telling me in which direction of travel I need to go. So I've got that. I've got to get power out. I've got to get the fuel self-sufficiency. I've got to make sure it's maintainable. I've got to make sure that I've got development flexibility, that I haven't painted myself in a corner, that as this is a first of a kind. So it's going to be, we will make discovery along the way. I've got to make sure it's safe. I've got to make sure I've got a schedule that I believe in. And most of all, I've got to make sure that the cost warrants the investment. So this is my guiding compass. Of course, if I wanted to go much more, I could give you much more detail behind those high-level statements, but that just gives you an idea of the complexity of the space. So, like a Boy Scout, I have my compass, so I've got my set of metrics that I use as a guiding, so I have my purpose, very much value-led, looking at concepts and what value they have. I've got a decision architecture, just like when I go to the sandwich shop, I have got a series of questions that I have to answer to enable us to come up with a design. So I'm very much decision-led. And then with my Boy Scout mentality, I'm out exploring. So I've now got a design methodology that enables me to go out there and explore using my compass and my map to explore the space. And that's exactly what we've been doing over the last 3 years. In 2021, I started off by doing a lot of technological landscaping, looking at the technological space of what options I had. So, you know, going back to my sandwich, did I have brown bread, white bread, hybrid bread, all of these different technologies that I explored. And then I started to imagine different design families, different tokamak concepts and plant concepts, using different system architectures. And then using those guiding principles, those plant attributes, then started a natural selection process. And it sounds a bit Frankenstein. Some of those design families retired quite quickly. Some we put on ice. Some we like bits of them, and we hybridized them together and then took them further. And then we went through and we got to a space in 2021 where we got a design envelope, and we had still some optionality to go forward. And we've just recently gone through another review where we are looking at what the integrated, as we continue down that decision architecture, what the concept looks like against those key attributes. And it's still work in progress. We're working in an emergent space. Those of you that are designers know that the more detail you get, it doesn't always get better. So it's a snakes and ladders, sometimes 2 steps forwards, 3 back, but as long as you're still making progress, even sometimes when we have to retire things, we've learned something in the process, and we can capture that. And of course, as a designer, I'm not just designing, if I was thinking of an aeroplane, I'm not just designing to be up at cruise. So in plasma speak, this is at the flat top. I've got to also design as I go taxi down the runway and get up to speed to get up to cruise altitude. And I also have to get down safely on the other side as well. So the design point is a moving target all the time over the pulse. The machine itself, you talk about aging gracefully. I mean, the machine, I can design it with its attributes on day one, but over time those attributes will deteriorate, age, and we need to make sure that the design is sympathetic for that aging as well under neutron dose, particularly irradiation, and the machine will deteriorate over time, and there will be consumable parts that will need swapping out. I also know that I have to construct it in a certain sequence and build it in a certain sequence, and that it's a first of a kind, and so it's a step by step. We're going to slowly operate this machine and understand, and as we understand more and probably calibrate our models into the real world from our idealized place, we're going to learn more. So again, this is an evolving design, and we have to manage it through the entire journey. And those of you that have done that journey, and probably just like me have got a few scars on your back, you realise you can't apply the full thing from day one, but you have to do it with an idea of when you phase it in, and you've also considered it from the get-go. It is first of a kind, and so we're going to somewhere which is very new. It sounds very Star Trek, going to somewhere where no man's been before. But again, we're going to somewhere where we have no physical tests, and we can't demonstrate necessarily what we're asserting by physical tests. So on this 4-box model here, you've got known physics, unknown physics, and physical tests, and bits where we can't do physical tests. We're in the very worst box, which is radical uncertainty, so it's likely that we're going to get some unknown physics that we've never seen before in our journey across to this new space. So we're extrapolating into a new space, so we're in this position of radical uncertainty. So that's one aspect of complexity. The other aspect of complexity is this is a massive system of systems. It's a cobweb of systems, and just like a cobweb, some are very strong links between systems, and other links are only slight links between the systems. So when you touch parts of the system, different parts resonate, and some of those relationships we don't truly understand at the moment. We've got assumptions and assertions that enable us to progress, and as we know more, we'll be able to put in those construction lines a little heavier because we'll know more. And those of you that have heard Ian Chapman's 6 great challenges that fusion has to crack, I can sort of chart on the left-hand side of this diagram. You've got the plasma physics, the diverter, which is the plasma exhaust, and the materials. Those are all areas with radical uncertainty because we're going to spaces where we've never been before. The conditions we're going to, if you liken it to an engine, we've very much been in a starter motor aspect, so you've just started to try and get your engine to catch. We've not got to ignition point yet. That's what ITER will do. So we're going to go into new physics in those regimes. So our extrapolations into a burning plasma and what it's like in a power production mode is very much an assertion, and we're in this radical uncertainty area. But again, this is somewhere where I'll assert that 7, the digital, is a way that can help us traverse this space, along with some physics theory as visionary as to what we see going ahead. And then the complexity part, which is the second part of complexity, many moving parts, that's in the integrated engineering. So again, it's looking at how we traverse that complex space. And some of it will be relatively simple. So going back to the diagram before, some of it will be relatively simple because we understand it. It's not all complex. Some of it we'll be able to take a bit of an experimental, agile approach. Other bits we can apply some systems engineering, but most of it will be adaptive and evolutionary. And that's how we need to tackle the design, and making sure that the design is sympathetic to that emergent space that we're going to live in. And I've talked a little bit there about in silico qualification, because we won't actually have physical mock-ups of the total integrated machine. It is a prototype, so we will be doing it first of a kind. But we do have now to model from a plant level all the way to the top of the machine, sort of system, whole system. We have models for that all the way down to atomistic, all connected. So there is a way that we can start to get that sensory feeling through this emergent space, and we can run scenarios and we can say what happens if it performs like this, what happens if it performs like that, and then we can traverse this, the design space by doing these what if type scenarios, looking at areas where there are opportunities and areas that we need to avoid. But again, it is a sensory type experience, and we are using these design experiments. We are using physical experiments where we calibrate our digital models to the real world to try and justify and substantiate our designs. And just like I was talking about with decision architectures, it is snakes and ladders a little bit. On this diagram here, I'm just talking, and it's a cartoon, please don't read too much into it, but it just talks about, as you consider different aspects of the design, how the decision architecture you go through, they're all connected, and you can come to one decision, undo that decision, and then you have to go back and look at how it affects other systems. On this diagram here, there are certain aspects that we're looking at with the design which affects the size, and some of it is around making sure that we get all a net energy out of all of the machine through the entire process. So understanding that environment and having those strategies about how to deal with different ways that twist and turn as you go through a discovery phase, let's call it a discovery phase, is really important. And a friend from ITER, Neil Mitchell, captured it. He pioneered the superconducting magnets on ITER, and he was just sort of talking about the fact that you need almost like a FMEA, failure modes and effects analysis, to understand what all of those relationships are, to help you plan and have escape routes, because as you go through a pioneering discovery, you will find out things, and you do need to have a plan of what happens in those eventualities. And it's so important. So it's plan, and scanning with those scenario type analysis of where you're at. And this is just me and my post-pandemic mind. I say I've caught the step virus. So this thing that I've got with a self-consistent design and all these systems that fit together, it is like a virus, and like most viruses, they will, as I sort of say, that as a designer, we know the more details you put on these things, the worse it gets, and it mutates and changes, and I have to have an antibody system that will fight this step virus that I've got. And so it is a little bit about developing new theories and applying those in the space. It's about working in a digital connected way and collaborative way across the space. And I have seen with many of the problems we face on the program, it's not a materials scientist, it's not a engineer, it's not a technologist, it's the combination of those and serendipity, that it's the multidisciplinary aspects that has often solved some of these crises. And I love it because you need a good old-fashioned crisis for the sleeves to get rolled up and the barriers between communities to drop, because they all get their IQ around a problem and solve it. And we've had a number of examples. I've just got some examples there around coolant choices on the in-vessel, something about the inboard on the exhaust, which is a critical aspect of the design, and remote or remountable joints, superconducting joints. Again, these are multidisciplinary type problems that we try and solve together. And that comes down to culture. So the culture on the program of pioneering and discovery and working in a collaborative way with both industry, private fusion, academia, as well as our own organisation, is something where, and yes, expect some failures along the way, but actually those scars that I've got on my back, those painful scars I've got on my back, which has caused me to go grey and bald, is really valuable, and it has a huge value to the programme and to the wider community. So it is a cultural thing as well as just the mechanics of what you need in place. So just to summarise, and these are some bits I just want to emphasise. Being the aged person that I am now, it's highly unlikely I'm going to be in the control room pressing the start button for this new first-of-a-kind power plant reactor, but it could be you. And I just wanted to emphasise it could be you, and you could have a part to play. We are pushing technology so hard to make this machine work, and there will be new technologies that come online. I think it's interesting in very complex system problems, it's the interfaces where the rub is and where you see the magic, the interfaces between all of these divergent requirements and divergent systems. And that's where we're going to make some real discoveries and I think find some new solutions. It's about gearing yourself up for emergent behaviour, not necessarily the solution you have in front of you at the moment, because it will adapt, evolve as you work through it. So again, having those capabilities on hand, and I'm not going to say it's just UKAEA, it's a multi-organisation, multidisciplinary. You need ingenuity. It's not just the technical community that need ingenuity. The commercial people, the project management people, the cost people, the schedule people, each of them needs ingenuity about how we're going to get our heads around this particular challenge that we're facing. And so that's very much gearing up for emergent behaviour. In a first-of-a-kind space, it's so easy to say, well, what if this? I don't know this, I don't know that. Well, my experience is make an assumption, make an assertion, get going, and then either retire that assertion, hypothesis, or you provide evidence to support that hypothesis, but you are getting going. Make assumptions and turn those assumptions into requirements is a key aspect of traversing this conceptual phase. And you saw my hamster wheel. It's about managing compromise. It's really important about keeping everyone engaged and connected, but it is a shared pain, unfortunately, because we all have to compromise a little bit. And I completely think that it's a multidisciplinary endeavour, so we need all of the disciplines working together in unison. I've probably said too much, rabbited on for too long. Hanny's shaking her head at me.
No, thank you very much, Chris. I think that was an excellent presentation. Because it was the more technically orientated one, we have a lot more highly technical questions in our chat. Don't worry, nothing that you won't be able to answer. But I do want to encourage everyone. I'm mindful we do have a quite varied audience, and we obviously have Fusion expert in the audience as well as members of the more general public. So I'm mindful, even though a lot of the questions are a bit more detailed, technical, if there aren't more broader questions, I will bring one in towards the end, just be able to make sure we are able to take everyone along on the journey. So the first question comes from Tim Nethercott, who said, does the step design have much in common with a jet design or operational experience?
So does it have much in common? I think what I've tried to do is, just like I was sort of, the JET team, an amazing resource of technical minds that have real lived experience working their way through lots of these problems. So actually, we've got a concept of operations that we've developed as part of STEP. We've got the operations team from JET to describe as a starter for 10 about what we think the concept of operations is. So building in those lived experiences, building their lived experiences all the way through into the requirements for the systems. We may not necessarily apply them from the get-go, but at least planting a seed so that you've got a strategy about how you embrace it later down the line. Does that answer the question?
I think it does answer the question. I would have said for the lay people in the audience, concept of operations means...
So in terms of for the lay people, concept of operations is just what's your vision of how you imagine the machine working in the future? And the different modes and states of the machine, whether it's you're operating in power generation, or are you in a commissioning phase with partly part installed systems, not all of the systems working, all of those aspects. It gives you all of your vision of how you imagine this thing working.
Yeah, thank you, Chris. No, there have been multiple other questions. I didn't realise Robin would have any question that he didn't already know the answer to, but obviously which coils are resistive and which are superconducting on the STEP programme?
So we have at the moment, because I keep saying, with our best knowledge at the moment, so we do have some resistive coils for some of the control coils in the machine. These are the ones that control some of the plasma elm control and things like that. We also have a resistive one just for the initial startup.
Maybe, obviously Robin has a strong fusion background, but for the people who don't have a fusion background and don't even understand the point of what's the main difference between resistive coils and superconducting coils, and why do we care about using one or the other in a different environment?
So, I mean, superconducting are very scarce materials. From when I was talking about energy efficiency, superconductings have no resistance, so therefore you don't lose a lot of power in the powering of the magnets. If you have resistive ones, they use more conventional materials that may be more tolerant to conditions, and you can recover some of those properties. But when you have superconducting magnets, again, we spend a lot of time where we position them and how we shield them from the environment, because they are, a very sensitive material, and any perturbation could mean that it goes unstable, and we have challenges.
Yep, thanks. I think that does answer the question. So the next question from Sean is, what role have supercomputers taken in the discovery stages?
So I'm going to be completely hands up honest about this. We have very much human in the loop, let's say, knife and forked our way through the design, very much trying to connect. We have a design workflow now, and we do have different digital platforms that we have now connected together to have this production line. So we've assessed over 60 plus concepts, and that's building them virtually as a digital shadow. Because it's been very clunky, let's say, in this early stage, in parallel we're looking to start to automate that process, and then from that automation of that process, thinking about imagining in the future, getting intelligence behind that also. And that's kind of where we want to get to, and that will be something that we will need going forward, because I think we'll constantly need, as new information, we're in a discovery phase, and as the fusion community, with new machines coming online, we're going to get new information, just like an open wound. It'll be like salt in my open wound when new information comes on and says, I'm just about to get this new thing on the boat to go to site to be fitted, and this new information has said we might need to change that system, and we need some reference point. So I think having highly automated design workflows that can assess new information, work out what the impacts are in an overall sense, doing that quickly and coming up with the best compromise will help us a lot in the future. So it's something that we're developing in parallel. We're not quite there yet, but that's our ambition to get there.
So obviously supercomputers are something that is more a modern thing rather than a long-term thing. Do you have a lot of experience from other programs in the past? In your experience, have you seen supercomputers being introduced much earlier in designs, or is it very normal for programs to build up their supercomputing capability as more technologies arrive and we're building capabilities?
It's almost been used as a bit of a diagnostic, I think, in terms of it's used to support experiments, saying, oh, we've got this, what's going on here? Let's start to apply some firepower to understand what's going on and calibrate our models. And is it a numerical thing? Is it a missing physics thing? Is it a computational thing? Again, it's being used as very much a tool now, as opposed to in the past it was just something that we dreamt about, but it's actually being used on experiments to sort of understand the symptoms we're experiencing.
Yeah, thanks for that. So the next question, again from Robin, is what's the runtime pulse length predicted?
So the good thing, which I didn't really emphasise, is with spherical tokamaks you can have continuous operation. I can't remember, is it the runtime? I think we're talking 6-8 hours at the moment, but
for commissioning.
Yeah.
Not for power production.
Power production, it could go continuous, couldn't it? In theory.
Yeah.
Because we don't have the same bounds that a conventional aspect ratio machine has, where it has to be pulsed.
Yeah, yeah. And there's another much longer question.
Ooh.
Do you review the life cycle cost analysis of STEP? Oh, I'll love you to answer this. So the social and economic impact
You're
is
having fun, aren't you?
I'm having a lot of fun. I would have asked a question on cost if there hadn't been one coming. Yeah, so thanks, Adam, for that. So the social and economic impact is significant, of course, whenever environment and the material and funding burden over time should be kept an eye on, and I can assure you there is, not just Chris. Highlighting interventions early on or throughout the research could be very impactful for the future, the circularity of tungsten.
So I think, yeah, I mean, there is a bit of a trade, isn't there, between capital cost and operational cost, and we're really seeing, because I could put my blinkers on and just say I've got it under the wire for the target cost for the capital, but knowing it's a nightmare for operational aspects because you've got a high turnover of consumables, which are very expensive consumables. So we're trying to have a more of a holistic. Again, it's very early stages at the moment, relative costs rather than absolute costs, but it's starting to feed in some of those aspects so we can start to make strategic decisions about where we want to pitch it, but recognising we don't have absolutes yet.
Yeah, yeah.
I'm looking at you because you're the cost queen, aren't you? So,
so for the people who've missed it, I'm in charge of the costing team. Oops, sorry, microphone, for the STEP programme, and I'm very much hoping we're having a big cost conscious programme because that is my role. So we're absolutely thinking about it, but I'm the chair, I'm not answering the questions, and I'm very happy for our chief engineer to be answering the question on my behalf.
Yeah, so I think, as we sort of said, we are asserting that it's a reduced cost machine, but it isn't just capital cost. There is the operational, which is something that we're really quite agonising about at the moment.
Yep, yep. There's another question from Mirza. Are you already developing the artificial intelligence that will control the machine?
Again, there's been some great work, isn't there, within the fusion community. I'm thinking of
UKAEA.
Yeah, and Marco de Bar et al. That are looking at control systems that learn. I mean, personally, I think it will help. I'm thinking the exploitation phase that we will be able to target the way we operate the machines much more quickly rather than just relying on a bit of a fishing trip and luck and then just getting the feedback. You could be much more targeted about the way you exploit these machines. So I think AI has a big role to play in that efficient and effective use of experimental time as you learn how these machines behave for the first time.
Yeah, thanks, Chris. I'm being reminded of the time and being a horrible chair. We've got.
That's why.
I know there are more questions. Really great. We've got questions, and also if people have questions afterwards, please do send them. Do send them to events@UKAEA as well. .co.uk. Kate will be putting all the emails in the chat so that you can contact us afterwards. We will be answering all the questions that come up at later stages. So thank you very much, Chris, for answering all the lots of questions that have come up.
No problem.
So our next speaker is Sally Forbes. So Sally Forbes is the Fusion Safety Advisor at UKAEA. She's got 20 years of experience in nuclear, especially around safety in particular, and her current role is supporting the UK government in the development of a regulatory framework for fusion. So without any further ado, I'm handing over to Sally.
Hello, Hanny. Thank you very much. Hello, everybody. We've heard a lot of the exciting things that are happening about fusion in the moment, developing our STEP programme, and also lots of the technical aspects as well. Now, there are many other things that we have to think about, and one of the important things is obviously regulation. So I'm going to talk you through how the current plant at Culham, the Jet Tokamak, another plant, is currently regulated as a fusion research and development facility, but then also focus on the work that we have been supporting the government with to understand what a regulatory framework will look like when we have these development plant. So as we've heard, one of the common reactions that we will use in fusion involves deuterium and tritium. Now, tritium is a radioactive gas. It's an isotope of hydrogen. In fact, both deuterium and tritium are isotopes of hydrogen, used in many different applications. Not all fusion developments will use these fuels, but most of the common ones do. So when we react the deuterium and tritium, what we get, as mentioned before, are lots of neutrons. They are what we want to capture to give us our heat for our power plant. And we get some helium. Helium, for anybody that's blown into a party balloon, those are what make your party balloons float. So helium is a very common and benign gas. Tritium, as I said, is a radioactive isotope, and neutrons also have, they're not radioactive per se, but they do either activate materials, they can cause damage, and they do create kind of gamma radiation as well. So we have to consider very carefully these. They're not insignificant safety aspects. They're very different, to state this, they're very different from the kind of levels of radioactive material, for etc., that you get in a fission power plant. They're very different from that, but they are not insignificant. As well as radiological hazards, you've obviously heard that we have very high magnetic fields. We have very high electrical fields and high voltages. There might be other materials we use, such as cryogens, liquid helium, for cooling some of these superconducting magnets. So we very much, when designing a power plant, at every stage, safety and environmental protection is taken into account. So we are one of those people that is making Chris run very fast on his hamster wheel, and other people placing requirements to make sure that we are protecting you and the environment as we go through designing our power plant right from the very beginning. So how are we regulated at Culham at the moment? As you've heard, we have the JET fusion research and development plant here and some other facilities. These are overseen by the Health and Safety Executive and the Environment Agency. So we've been operating, as you heard, for 20, 30 years or more, and have been very carefully regulated under the current regimes for radiological facilities. So under the Health and Safety Executive, their role is very much to protect people. That's both workers on the plant, but members of the public who happen to live around the plant, to make sure that any exposure that they get to radiation is kept as low as reasonably practicable. Obviously, in normal operations, these exposures are extremely low. There might be a small amount of discharges of gases, for example. But obviously they also have to look at what might happen in an accident situation. So you've heard safety cases mentioned. Those are a very detailed examination of the what ifs, of the very unlikely what ifs. And even if such a thing should happen, that there will be very, very small impact outside the site. So we actually hold a consent under the ionising radiation regulations, focusing here on the radioactive side because that's one of the differentiators of fusion. Many other different regulations look after the hazardous materials, electromagnetic fields, etc. We're also currently regulated by the Environment Agency, and they will be looking at any of the sort of low-level discharges we have, gaseous or liquid, production of any radioactive waste we have from the operations, and making sure that the level of protection to public and environment utilises something called best available techniques. It's making sure we do as much as we can to reduce those. So we hold a permit under the environmental permitting regulations. So those regulators on Culham site. We are not a nuclear licensed site. That's a very important thing to notice. We don't have fissile material, nuclear material and fuel, and we have much, much lower quantities of radioactive material, or tritium, so we are not a nuclear licensed site. But what happens when we have much larger facilities? We've heard a lot about STEP today. There are many other facilities around the world being developed as prototype and demonstration power plant. Not all of them, because there are many different technologies and sizes, but many of them will be much larger scale devices than we currently have with JET at Culham. So they might have a much higher power, which means we might get we should get a lot more neutrons, which will activate materials and make some of the components inside the machine radioactive. There will be a lot more fuel throughput, that's the tritium and deuterium gas, there will be a lot more of that on site. And jet pulses for a few 0.2 seconds several times a day, and we'll be talking about several hours or continuous operation. So the government and the regulators wanted to look into what is going to be appropriate for the future when we have these potentially larger plant. And it's really important to make sure that this is proportionate to the level of hazard, maybe a little bit higher than we have now, but a very different profile, to example, for nuclear fission power plants. But we also got to make sure that regulation is enabling, it's novel. As you've heard, almost things are changing on a daily basis, and then we've got a lot to learn over the next few years. So how do we make sure that regulation keeps up with advancements and isn't a blocker at all to technology, but very much keeps its eye on the safety and environmental aspects of that. So 2 years ago now, in October 2021, the UK government started looking at how we would, if we needed to develop anything in the current regulatory framework for these future demonstration plant. The first thing it did was gather together a body of experts. They're called the Regulatory Horizons Council. There are a number of independent experts that advise the government on new and novel technologies and how the existing regulatory framework in the UK might follow through on that. So they made a number of recommendations. We in my team also supported the government in something we call the technology report, and all of these are publicly available online, where we looked at what the difference between a fusion power plant and a research and development plant like JET might be. So we took a lot of independent research that had been done and collated that to look at the level of hazards. So those were some information that fed into the government papers. So a consultation was held, a public consultation, where the documents that you can see on the screen about the fusion energy programme and proposal for regulatory framework. There were over 60 respondents to that, members of the public, members of the fusion industry, academia and other fusion stakeholders around the world. Those responses were all collated together and published in June last year in a response to that consultation. Now, the decision made by the government based on the advice from the Regulatory Horizons Council, the scientific work we performed at UKAEA and all these responses was that actually the current regulators of fusion R&D facilities will retain the responsibility for these fusion demonstration plant, i.e. the Health and Safety Executive and the Environment Agency, or their devolved regulators in the different nations in the UK, are the appropriate regulators to continue. So that has just been legislated against. Many of you will have heard of the Energy Act that was passed in Parliament a week or two ago. That has a clause in there that specifies that fusion will be treated differently, and we will not be treated as a nuclear licence site in the future, either at JET or somewhere like the West Burton STEP site. That's really important because it gives kind of like certainty and confidence to the industry, even though we're 10 years away from starting to build, 20 years away from operating the STEP facility. Other facilities might come online a bit quicker from the private companies, and it's really important that they know what the framework is. So just to summarise on that, the UK is taking very much a proportionate approach to regulation of fusion power plant and demonstrators. We've looked at the hazards. We acknowledge there are some novel hazards in there. There will be different types of radioactive material, but they are very different to what you have in a nuclear fission power plant. So the UK government consulted on this in a public consultation and made their decision based on evidence provided by institutes like ourselves, independent advisors, and the comments made by people on the consultation. This approach very much considers the hazard and complexity of fusion power plant and makes sure that protection of people and the environment is very much at the forefront of development. So we've been working with the regulators, we work with industry and technical experts. We do a lot of work with the International Atomic Energy Agency on this because we've not just been doing this alone in the UK, it's very much an international effort to look at what the fusion industry will be like around the world. So we've very much been sharing some of those ideas across the globe. So as well as all the technical side to fusion, there are lots of support areas and in particular very important is making sure that as we develop and eventually operate these, there will be the highest priority on safety and environmental protection. So thank you.
Thank you very much, Sally, for all of that, and I'm sure there'll be more questions coming in. I have a question at the beginning because we've talked about costs before,
Yes.
and obviously there is that kind of continuous tension that you want a power plant that is very safe, and you can make things extremely safe by putting bulletproof glass into windows and 50 locks at the door. But at some point we recognise we're not doing that regularly at our houses because it is overkill and it would be very expensive. But on the other hand, we have the cost of living crisis, so the cost for energy is really important, but especially with new energy sources that are experimental, and you talked about the need for innovation. I think everyone's always in that bit of the weird tension space of, I want it to be very safe, I don't want it to be very experimental, but at the same time, I don't want to be wasting money on being overly safe because it's my taxpayers' money that will be wasted in that regard. Can you just help us give maybe examples or outline more clearly how we're trying to draw that tension and try to navigate in the right space without being overly conservative, but also being safe enough that no one needs to be worried that would be cutting corners?
Absolutely, and that's one of the key basic principles of regulation, certainly in the UK and throughout most of the world, is that concept of making risks as low as reasonably practicable. There's a lot of effort goes on throughout the whole design and STEP has significant sort of safety and environmental teams working with it to understand what could go wrong, what the consequences of that would be, could there be any releases off site in a major accident situation, what's the likelihood of that happening, once in 10,000 years, a million years, we go to that kind of level. So you look at kind of what the risk of something happening is, and if it's a relatively low risk, then you make that case that, yes, you don't want to over-engineer your safety systems because what you're actually doing is preventing operations in reality. And thinking about part of the decision about to continue under a sort of health and safety radiological framework rather than a nuclear fission plant framework is some of those requirements for nuclear plant are just not required for fusion plant. You might over-engineer it, as you say, you might put so many constraints on it that A, you're spending money that isn't gaining you any benefit in terms of health or environmental protection, and may constrain your operations, because in the end of this, what we're trying to do is enable an industry that will help us in our green environment. So we've very got to make it feasible, but whilst making sure that safety and environmental provisions are appropriate to that. Yeah.
Thanks very much. You've also mentioned at the end of your talk harmonisation and global harmonisation. Do you want to be a bit more explicit about how the role of the UK is helping with that and how that's different from other environments where we obviously do not have a global harmonisation?
Absolutely. So fusion research has very much been an international field. If you think things about the ITER, which is the experimental facility currently being built in France, many programmes have development programmes similar to STEP, sort of demonstration ones. If we ended up with different types of regulation in different countries, that really again doesn't help the global deployment of fusion. So, for example, in France, ITER was starting to be developed about 15 years ago, before there was a particularly large thought about fusion power plant. ITER is actually a nuclear facility under the definitions in France that has potentially, imposed some requirements that are quite onerous on it. So what we want to do is work with those countries that are developing fusion programs, understand how you get that best balance between looking at the different hazard potential of fusion in related to fission, not just assuming that it's the same. For many of the aspects you've just mentioned, we want to make sure that we get the cost balance right whilst maintaining safety. There's a lot of expertise around the world, and it's really fantastic community coming together to consider safety and environment, as well as pushing the development forward.
Yeah, thank you. We do have a question from, we have two questions from Tim. Can you consider the tokamak to be inherently safe? That is, if you remove the power input of fusion reactions, will they cease quickly?
Yeah, that's very much one of the things that is different to, for example, a runaway critical reaction that could occur with fissile material. You put very small amounts of fuel of the tritium and deuterium gas into your reactor at a time. It's a kind of continuous flow, but a very small amount, and it takes all the effort to keep that reaction going. Any slight perturbation, and that's completely correct, that reaction will stop, so you can't get that runaway action. So in that way it is inherently safe. So what we're mostly focusing on is the fact that you do have tritium gas in the plant and other parts of the plant if there was a leak in a different part of the plant, for example. So yes, it does have those inherently safe characteristics, but we do consider those radiological materials like the tritium and some of the activated components as well.
Yep. And you might have already answered most of that. Tim had another question around the ITER, whether ITER has a similar regulatory regime as been proposed in the UK.
Mentioned that it is just a bit different. The legislation is different, and again, where most of our countries made the legislation for fissile fusion fissile plants 30 or 40 years ago, we weren't really thinking about fusion, so it was forced down a particular angle by the regulatory framework in France. However, again, it's a balanced approach, what we call goal setting, that you make arguments that the hazards are not the same. So you do get some similar outcomes, but I think in some way it has been very difficult to fit that, and we're all learning kind of lessons from that and very closely working with ITER on how it went about that.
Yeah, thanks for that. I think we have one final question before we're finishing the seminar. But really, for anyone who might be concerned about any safety standards or the development of the safety cases and the regulatory regime, are there contact details either from the government or from UKAEA that people can contact if they have further follow-up questions or any other concerns that they want to be raising?
Yep, so obviously if there's very highly technical questions, that's something you could come through the address that I think we have on there to come through to us. We are working closely with the regulators. They're on site quite often, familiarisation and training and things like that. So I think if you want to come through us, we can make sure that gets on to anybody. But what we've heard today is that we're involved right at the beginning. The regulators are thinking about it right now and learning and looking at issues. We don't wait until the day it's going to be turned on. So thank you.
Yeah, no, thanks very much, Sally, and obviously to all of our other previous speakers. My apologies for the people who had a misunderstanding. I think we've had conflicting information whether we're finishing at 3 or at 3:30. So thanks everyone who's been able to stay and who've been showing interest in our presentations. There are obviously opportunities that we've mentioned before to be getting in touch and staying in touch. So thanks again everyone who's participated in this Future for Fusion seminar on the Energy and Security Green Infrastructure webinar that we've had, and enjoy all the upcoming presentations that will be held as part of this week coming tomorrow. Thanks very much.